Hello, everybody, to all the persons that are joining the webinar. We will be in a few seconds. We are letting the different participants to join the session. Hello, we begin the webinar. Good day to everyone attending this webinar and welcome to the presentation. My name is Dora Blanco. I'm a full professor at the University of Santiago de Compostela in Spain, and today I will serve as the moderator of this session. I am representing here the Earth Science Informatics Technical Committee within the IEEE Geoscience and Remote Science Society. And this is the committee which is organizing the webinar. I also co-lead a working group in high performance and disruptive computing remote sensing. And I will share with you in the chat a link to know more about these working group activities. The information is in the webpage of IEEE. And as part of GRSS over the past 5 years, we have organized a school, a summer school that has become a venue for networking among students and young professionals and researchers related to remote sensing and high performance computing. We have studied different issues on cloud computing, quantum computing, or GPU computing during the last 5 years. And this year we organized again this summer school that will take place at Santiago de Compostela in June of this year. I will share also with you in the chat a link to know more about this school. We will receive this year 30 students. Today's speakers have previously participated in our school with great success. In this webinar, and they will discuss how to accelerate remote sensing workflows using Google Earth Engine, a cloud-based platform that provides access to Google's computational infrastructure and that enables planetary-scale geospatial data analysis. The persons who participate today will be presented after a very short video that is the main information of these webinars. I'm trying to share the screen to show you this short video, and then I will present the speakers. Thank you.
Sorry, Dora, I think I can't hear the video. I don't know if the others.
Sorry? Yeah, I tried to share it again. I had some problems with the sound. I tried to share again.
I know that last time, I believe, did you mute yourself during when we were showing before? Maybe that will help.
Welcome to today's IEEE Geoscience and Remote Sensing Society webinar. We're so glad you're joining us. United by the mission to advance geoscience and remote sensing, GRSS is dedicated to knowledge sharing by ensuring transparent, accessible, and collaborative learning for all. And our webinars are just one way we bring that commitment to life. Designed for students, early career researchers, professionals, and enthusiasts. These webinars address foundational topics as well as a wide range of emerging subjects, while also offering sessions on academic writing, publishing, and career planning. Our webinars are made possible through the collaborative efforts of GRSS's technical committees and various other initiatives, bringing together a diverse community of experts to deliver high-quality learning content. During the webinar, please submit your questions through the Q&A feature, and they'll be addressed at the end. You'll be asked to complete a survey afterwards, which helps us tailor content to your interests.
Hello again, I'm sorry for this problem with the sound that was finally solved. Now I will present the speakers that will talk today. The first one is Izquierdo-Verdiguier. She has presented this seminar in other in previous venues of our summer school. Is a scientist in the Institute of Geomatics at the University of Natural Resources and Life Sciences, the BOKU University in Vienna, and he's working in Earth observation data and cloud computing environment for land surface technology. And she is a Google developer expert, and it's the reason she's here, appointed by Google to present this webinar. The second person is Álvaro Moreno Martinez. He is also PhD and professor at this moment at the University of Valencia in Spain. And he has participated as Emma in different projects, and he has obviously different publications. You can see all the details on their biography in the information related to the webinar. And the third person is Smit, is a doctoral candidate at BOKU University in Vienna, and he is researching in evaluation of sustainable agricultural management practices in Austria. And they are very experienced, obviously, in Google Earth Engine because they are experts and they have the experience teaching and researching using this tool. I'm very grateful because they have accepted to be here. Thank you to all of them. And they will begin now with the presentation, sharing the screen. And you are allowed as attendants to this webinar to write the questions in the chat. And at the end of the presentation, I will read the questions, so they, Emma, Álvaro, and Eric will be able to answer to these questions. Thank you very much for being here, and Álvaro, Emma, and Eric, you can share the screen when you want. I'll mute my microphone, but I will be here attending the session, obviously. Thank you.
Thank you, Dora. I'm waiting. Yeah, thank you, Álvaro. Yeah. Thank you very much, Dora, and thank you to the GRSS for inviting us to do this webinar. As Dora said, I'm Emma. I'm going to do a short introduction about what is Google Earth Engine and the interest in to use this type of application when you work with remote sensing data. And after that, my colleagues Álvaro and Eric will present an example of using Google Earth Engine, a real example that we prepare for you. So next slide, please. You need to consider that nowadays there are a lot of different types of satellites around the Earth orbiting and acquiring a lot of information and a lot of data from the Earth. The last data that I have in 2021, more than 700 of different satellites was focused on Earth observation. So in this case, next slide, please. In this case, the use of cloud computing is important, and how affected the use of this type of platforms in the field of remote sensing is that, next please, we pass from different small tiles and different patches of images working in our computers, in our servers, in the lab. And then we move to the next one, please, to create different maps at global scales using the cloud platforms. In that case, also it's available to use different type of source, different multi-sensors in order to produce different type of global scale maps. So that requires to use a lot of data, and for that reasons nowadays, next slide, please. There are different type of platforms focused on processing data, but most of them, some of them contain some remote sensing data, but in this case, the knowledge of the technological skills should be high in order to work with most of them. In that case, it's needed to know how ingested the data in the cloud, it's needed to know how deploy the virtual machines, work with the CPU or the GPU, and not all of the people that are working in remote sensing field have that type of skills. For this reason, at some point, application focus on geoprocessing, a cloud application focus on geoprocessing, is really nice to have in order to decrease that type of knowledge in the technological part. So next slide, please. In that case, at some point, appeared in 2012, Google Earth Engine. And can you click again, please? And at some point, as in the paper published in Remote Sensing of Environment in 2017, is an application that make easier the monitoring and track the management in the Earth. So in this case, the application has a vast quantity of data and a lot of computational power, and integrates different deep learning technologies and have easy access to different type of scalable infrastructures, specifically from Google, as can be Vertex AI or can be BigQuery. Next, please. So at some point, what is Google Earth Engine? It is a platform that provides a lot of data and leave us to analyze different large scales part of the Earth. And is mainly contains two different components. One is the data collection. I will show some information later in the next slides. And also have a massive computational power. That is because it is an application that behind of it is using the infrastructure and the powerful of Google Cloud. So at some point, the application leaves us to specify different operations that we wanted to execute in Google Earth Engine. Next slide, please. So considering the different type of data that we can find in the application, there is a big data catalog that it is composed more than 70 petabytes of data. And in that case, we can find different time series, as can be a Landsat or Sentinel, which they have different spatial and temporal resolutions. Also, we can see or we can use and analyze the MODIS temporal series, coarse spatial resolution, but higher temporal resolution. But not only we can focus in reflectance products, also there are different type of vector data, land cover and terrain data, and of course also we can find weather and climate data. That data set is the official data set from the Google Earth Engine application, which every month include more than 2 petabytes of data in the repository. Next slide, please. But if you don't have enough with that quantity of data, for sure you can look the EWOSOM database. In that case, it's a database created by Samapriya Roy, who is a Google developer expert. And I would like to take the advantage now here to thank him about all the huge work that he is doing with this database. This database is consists on different type of remote sensing products that people developed and created in Google Earth Engine, and it is ingested in the cloud in a different ways. And has the scientific support, because all the products already published there has the support of one peer review publication paper. So in that case, you don't have only the 70 petabytes of the official catalog. You can find much more petabytes of information in this database. Next slide, please. But focus a little bit more in the core concepts of remote sensing, and most of us are focused in this webinar in remote sensing data. I'm going to pass to explain the 4 main objects that Google Earth Engine contains in order to work with geodata. Next slide, please. So the first one is an image, and in that case, the object use it in order to utilize the image is ee.image. In that case, we can have the reflectance values of our image, we can have different quality flags of the images, and we can calculate, for instance, the NDVI and also have it as a new band in our image, including in the image. As the same that we have rasters, next please, we can also use vector layers, and in this case is you can see the ee.future is the object that we use it in order to use geometries. And in the example, you can see that the geometry is a point and is provide the coordinates of the points. And also you can have including into them different type of properties, which are information related with the different geometries that you can have. But we are talking about remote sensing data, and for sure we can have different type of acquisition. So next, please. We can have it an image collection. And in that case, image collection is not only related with temporal acquisitions, temporal series in some specific area. As you can see in the example, you can have different type of acquisitions that are overlapping at some point due to the orbiting of the satellites around the Earth. So in that case, the image collection can have that type of images inside that cover different spatial regions, but they are acquired more or less in the same time. Or, next please, you can have different time acquisition in the same or in a specific study area. And in that case, you can also contain them in the image collection. Next, please. Also, in this case, it's possible to visualize the different temporal profiles of the different images that are containing in the collection. Next. As at the same that we have the image collection, we can have the feature collection, which is the last object that I'm going to present today. That doesn't mean that there are not more than there are not more objects that I presented. For sure there are, and you will see later in the example. And in this case, the feature collection is a set of different geometries. The feature is only one point. In the case of the feature collections, you can see that we can have different points with the different properties associated with the different type of geometries that we have in the collection. Next, please. So what we can do with Google Earth Engine, we can load an image collection, we can use different filters in order to filter the clouds, we can apply different statistical operations, and then we can create a final product at some point. So this is the simple example that we can apply or we can use in Google Earth Engine. But at some point, there are different things that we can also do with more complex operation. And now we are going to show some examples that were developed by ourselves using Google Earth Engine. Next, please. So the first one is the ground primary production over the contiguous United States in a daily case using different time series as Landsat and MODIS. In this case, you can see the animation and is all the information you can find in the paper associated to that one. In that case, you need to consider that each image of it are moving millions of pixels at the same time in order to be produced. Next one, please. Another example is the start of the spring. In this case, the temporal series increased a lot because it's from 1950 till 2020. And each image also contains a lot of information, and the quantity of the pixels in order to produce here, we are talking a lot of millions of pixels too. So these two examples are two clear examples that we cannot produce this type of products in our own laptops. So it is required a cloud platform in order to produce them. Next one, please. Another example is was produced by Eric. In that case, he developed a processing chain in the Google Earth Engine in order to produce different type of soil properties. And next one, please. And the last example is a data fusion example. Can you, next one, please? That you can see a remote Sentinel-2 temporal series at the north of France. And in that case, you can see the temporal series of the original Sentinel-2 images. But if Álvaro click next, please. We can see the data fusion that we produce using Google Earth Engine and using 3 different types of data, MODIS, Landsat, and Sentinel-2, in order to produce a gap fill temporal series every 5 days in a specific area. In this case, it's an agricultural area. Next one, please. In order to produce all these type of products, as I commented, are complex, are not easy in order to produce, but you can find a lot of information in the reference, and you can get a lot of information not only about the cloud by itself, also you can find a lot of information about the different objects that the application has and the different functions that you can find in the different objects. Next, please. So if you would like more references, here in this slide, we presented 3 of them. One of it is, the first one is the cloud-based remote sensing with Google Earth Engine. It's a book wrote by different Google developer experts and also different Googlers in order to produce a good documentation about the different type of objects and different type of process that you can use, from analysis of temporal series to the visualization of the results. The second one is, is only for Spanish speaker, or nowadays with the new tools, maybe also you can use it. It's focused on Google Earth Engine and in an easy way to use the application. And the last one was a special issue that was done by MDPI, published in 2019. So next one, please. So as we talking now about Google Earth Engine, we don't want to lose the opportunity to show how to use it. This is the code link that goes directly to the application, and then you can type it in your computers. Hope you are Google Earth Engine users, because if not, it's really complicated to work with it. And if you are not already user, you can go to the Google Earth Engine webpage, and from there you can see how you can register on the application. And for the rest of the people that are already users, you can type and go to the JavaScript application. And now Álvaro and Eric are going to show you an example how to predict leaf area index in a global scale. So thank you for your attention. The floor is yours, Álvaro and Eric.
Thank you, Emma. So now it's time to get our hands dirty with a little bit of programming and to see how we can do this a regression example with Earth Engine. So, but let me first give a very short introduction about what we are going to do with this example. So I guess that some of you are familiar with what is a biophysical parameter. Biophysical parameters are the structural parameters of the vegetation, like leaf area index, fraction of absorbed photosynthetically active radiation, which is closely related with photosynthesis. And typically, these parameters are retrieved with very complex relative transfer models like ProSail. ProSail is the combination of two models, Prospect, which imitates or models basically how the solar radiation interacts with the leaves and the soil, and also there is another module in ProSail, which is SAIL, which explains how the canopy interacts with the leaves and the soil and everything. So how most of the remote sensing products that you can find these days are produced are using these kind of models, and they operate in this way. So you give traits or information of the vegetation, like for example, how much chlorophyll has the leaves of the trees, how many layers leaf area index has these trees, how this canopy is being observed by the satellite and the light incidents and all these kind of circumstances that could happen. And you put all these ingredients in the model, and at the end, it provides the reflectance data that could be observed by a satellite. So when we create these synthetic simulations with these very complex models, what the remote sensing people do is, okay, then we do the other way around, because we know that the satellites can measure the reflectance data. So we use the reflectance data that this model provides, and then we invert the model, and we can retrieve the chemical components of the leaves, or the parameters of the leaves, or the biophysical parameters of interest. So this is kind of the logic of how these biophysical parameters are usually being produced by the scientific community. So this ProSail model, if you want more information, is something that has been deeply documented in the literature, and you have tons of papers if you are interested. So if you write Prospect or ProSail, you are going to find a lot of information about it. So next, what we are going to show today is the typical steps that we're going to plan. So we have already created the lookup table that we want to invert. I'm going to show how we can do that. So the steps we need to do is we need to prepare the satellite data that we want to use. In our case, we are going to run this exercise for the example with MODIS reflectance data, MCD43A2, which is basically nadir observation of reflectance data. And we also need quality flag information. Why? Well, some of the examples that Emma showed before is that many times with optical data, we have clouds, haze, atmospheric contamination, snow, and so on. So we need to use this quality flag information in order to remove the data that we are not interested in using, right? Because we want to retrieve something of the land surface related with vegetation. So we want to remove from the reflectance signature of the MODIS satellite anything which is unrelated with vegetation surface. So after that, when we have this clean reflectance data, filtering out what we don't want, then we will use a typical machine learning algorithm, a random forest, in order to invert this lookup table I showed before, and to show how we can do that at very broad scales just because we are using Google Earth Engine. Okay, so what I'm going to do now is I'm going to show you, this is where basically you have a Google account. This is what you are going to find. This is the JavaScript API, which you can do a similar thing also in Python using the Python API. But in my opinion, for starters, I think that probably using the JavaScript API could be better because you have everything kind of integrated in the same environment. So you have the map viewer here below. You have access to the documentation pretty easily here in the left side of the JavaScript environment. You can also see how many tasks you are being processing. You can also have information in the console with whatever you want to report, and you can even click and see what's going on in the maps. So as you can see in the documentation, every time you click on something, you have a brief but very useful documentation about what you want to do. And also you can see that I have tons of scripts here that I have produced. So you can have access to all your codes and you can organize it in the way you want. So, okay, with this brief introduction, as I said before, what we want to do here is we need to prepare the needed data. So we need to find the MODIS MCD surface reflectance data. So how we are going to do that? Okay, we know that the product is this MCD43A2. So in that way, if we want to find some data sets in Earth Engine, you just need to type here, for example, the data set you want to use, right? And you can see I have written MCD43, and I see all the data products which are available in Earth Engine. So because I want to use the MCD8 reflectance data, sorry, this is the quality MCD4. The reflectance data you can see when you click here, you can have a brief information about the dataset itself, information about the bands in class, and you have also a code snippet, which to directly include this data in Earth Engine. So you can click here and automatically, or here, but I can show here, and when I write here, I can access to the MODIS data can be ingested. So what I do there is I need to create a variable with this, which is the MODIS. Probably I'm going to speed up a little bit because I have already prepared this. Now I want to slow down here. And when I do here, what I have now, as you can see that nothing is happening, in order to check if I have imported properly the data set, you need to print what you have done. And then when I print and I run the code, Everything doesn't do anything unless you run the things. And you check when I have click on run, I have an error because I have too much data, because I'm just trying to ingest all the MODIS data set, which is a lot. So we need to filter out some of the data. So for example, we are going to work with a limited amount of data. More precisely, for example, we want to select a given year using this filter date function. And in that way, so I say starting and ending, which is the period I want to work with. And for example, it could be 26, 12, 31. As you can see now, if I filter that again, I need to add the dot. Caution, because you see that it changes the color. Now I can compute because I'm not using so many images, right? Okay, I'm going to speed up a little bit. So because we only want the reflectance data, we can select, because you can see that we have plenty features with every image. As Emma said, this is an image collection, but you have a list of bands. And I want only to select the nadir reflectance bands, which are observed from the surface. So you can select anything that includes the starting word nadir, right? In that way, as you can see, I run again. When I print, I see that they have obviously the same images. I haven't filtered any dates new, but now my list of bands only includes 7 elements, which are basically all the bands, reflectance bands I want to use, right? Okay, now we have the data we want. I'm going to comment this because I don't want to print out now that again. And we need the lookup table because we want to, well, I'm going to ingest also first the, sorry for that, the quality flag information. So let me ingest that. And this is the, I'm going to go faster now. This is the, in the same way, instead of using the MCD-A4, which is the reflectance data, we have ingested now the A2. As you can see, if I type here, the A2 bands corresponds with the quality daily band, which is what we want to use to mask out clouds and everything, just to keep the data clean, right? So in that way, if I print again, we can see that now when I print this variable, I have the same amount of data, but now the information which is available in the bands are these BRDF albedo band quality bands, but we want to use. So, but we have different quality bands for each reflectance. So we want to use the mean quality of all of them. So we want to compute the mean quality in order to mask out the reflectance data we have. So in order to do that, there is a very important function in Earth Engine, which is named map, which allows to run a function in every image of the image collection. So because we don't have too much time in the spirit of time, so I'm going to explain what this function does, but I'm not going to write it entirely. So you can see that I have the image collection. I filter the dates. I filter the bands I want, and I map this function here. What this map does, it takes the image I have, it reduces, which is a operation over all the bands of the image, and I compute the median value of the quality of all these quality bands, and I change the name of the resulting image as median quality flag. And at the end, what this function does, it takes the image I have in the image collection and it automatically adds as a new band to the image collection, or for every image of the image collection, the mean value of the quality flag. So let's check now when I run again this code, what they have as the results of running all of this. Okay, so now I have the same features, obviously. I have the bands, but I have, instead of 7 bands, I have 8 bands, where the new band is this median quality flag, which is the median value of all the quality bands that I have in my image collection. Okay, so we have pretty much the image collection ready, but the next step we need to do is, because in order to map function, we need to map over image collection. So we need to put together this image collection and this image collection. And in order to do that, there is a very, very nice function that was recently created by the Google people, which is link collection. And I'm going to copy paste the code here and tell what it does. So it takes the image collection that I have here with the reflectance data. And I said, okay, link this collection with the quality collection that I have here, right? Which is this MODIS MCD43A2. And I want to link the band's median quality flag because this is the one that I want to use. But because obviously I want, when I link this collection, that the time steps match together. So I say that I want to combine these image collections, paying attention with this property that I have in my image collection. You can check here that when I expand for one of the images of the image collection, all the properties, there is one which is this time start. This time start is a number which reflects basically the time where the image has been acquired. So in that way, when I run this piece of code here and I print what I obtain afterwards, you can see that my combined collection, which is what I'm showing here, has obviously the same images. It has, but now the difference has, sorry, I'm missing something here. Okay, yeah. But now I have the reflectance bands that I had, but I have added this median quality flag information that I will need to mask out my reflectance data in order to run my my code later, right? So something that I'm going to do next before showing how we are going to use the process data is I want to show you how we can see on the screen the results of or what we have in this image collection, right? In order to show something on a screen, we can use the map function, which is with this function we can show on the map below any image we want. So, for example, we want to show the first image in the combined collection here. So we do that and we say, okay, we want the first elements of this image. And because I don't want to spend too much time about how to because we need to equalize and select the bands to plot on the map, you can do that with a dictionary here when you say basically the parameters to visualize things. As you can see, I see the opacity. I want to be not transparent at all. And I want to select the RGB bands because I want to show an RGB image here in the map. And I want to limit the range of observation. So because MODIS reflectance varies between 0 and 10,000, remember that you have to scale the data in order to provide this. So if I do that, I select these parameters and then I name what I'm going to show on the screen like RGB. So if I run this code now, you can see that something is moving here in the RGB side, and you can see like I have a global image of MODIS for the first date I have in my combined collection. All these here you can see there is a lot of snow and problems that could happen with the reflectance data. Okay, so I said that I want to use this MODIS data, but I also need to mask out clouds and snow according to the quality flag information I have. So I'm going to speed up a little bit and I'm going to create a function which I'm going to explain now what it does. So what this function does is it takes an image of my image collection and I select the band that I have with the quality flag and I select anything less or equal than 1. Why I do that? Okay, yeah, because if you check the information of the quality flag information, basically a value of 1 or 0 indicates that the quality of the reflectance data we want to use is best quality, very good, or good. So we want to discard anything which is not reliable. And this is why we select as a filter that the mean quality of all the bands should be below good quality or best quality. Okay, this is the function we want to use. As you can see, you can use a function in place, or you can create the function and map the function afterwards. And how we do that? Okay, we can apply the function. Just basically, I'm going to speed up again a little bit. And we map this, as you can see, taking the combined collection that we have created here, right? The image collections, combined collection, and we map this function over the combined collection. And this is what let's check if it works as expected. Let's print again. And now, okay, we have our image. It seems that it's working. And now we want to check if we have actually masked out what we want. So instead of we are going to map again, I comment this because I don't want to, well, we can use both RGB, and we can now use this modis filter. And we name the new image we are going to map as filter RGB, right? Okay, so now you see two layers here, right? And you see how, oops, one, let me check this, is loading. One is more filtered than the other. So obviously you can see how actually we are discarding a lot of data that could be low quality and so on. So, okay, we have the remote sensing data ready to go. And now I want to show you how we, in order to invert the data, we need to have the lookup table. So we have ingested this lookup table by ourselves. It's basically a CSV file when we have the training data that we want to use for creating our model. And in order to do this, I have this data already ingested here in filter, where's it? Okay, yeah. This, as you can see, this is a lookup table we're going to use for training, and it has lots of features, as Emma explained, which are basically the results of ProSale, the bands that ProSale are providing, and two example biophysical parameters, which is basically what the ProSale had ingested for inputs in order to produce these reluctance. In order to do that, we are going to invert this leaf array index, and you can see that we have around 400 samples to create our machine learning model. If we wanted to upload our own lookup table, we just need to go to this asset side, and you can click here in new. And as you can see, you can click here in table upload, and you just say, okay, the name of my asset is this, and you just select as your CSV file that you can have in your computer, you can create, and then you can use this lookup table for training your model or any other thing you want. You can also import polygons and things like that. So in order to speed up the process, I tell you, you can see that the asset is here. The name of the asset is users because this is where it is available. I have done that for you. And the training features are imported in as a feature collection name like that. Just to run again to check if the feature collection is correctly imported. And it seems that, okay, I can plot the, show the first 10 elements. And okay, it seems that we are ready to go. So we have our data set ready. We have reference data ready. And so now it's time for Eric to continue with the machine learning part. Okay, Eric, I can handle to you now the presentation.
Thank you very much. Precisely. Álvaro, going to copy in the code snippets as I say them, I assume.
Okay, yeah, exactly. Perfect. Yeah, first of all.
Yeah. Okay, so to train a random forest to do the inverted processing from remote sensing data back, so to say, to the biophysical parameters, we first need to define the input names which we will give our random forest. In our case, those are the bands 1 through 7 of the there you go, of our input names. These are the remote sensing bands that the random forest will take. Then we need to make a new object, a new classifier object in this case. Random forest is implemented by default as a classifier, but as you can see, it's open as an ee.classifier, but you have to then change its output mode to become a regressor. So first, as a classifier, you define the number of trees and other parameters. It's very recommended for your own applications to really tune those parameters and not just use the default ones. In our case, we've set the seed and the minimum population of samples per leaf in each tree. You change the output mode, and then you input the training parameters. In our case, the features are the training features which were uploaded as a CSV. Oh no, sorry, as a CSV. Then the input properties are the 7 bands that we're going to use, and the class properties. So the biophysical, the target of the regressor is the LAI, in our case, the leaf area index. Then the random forest is set and also trained already on the features that we've given it. Then you can have Google Earth Engine explain the feature importance of the trained random forest to you. The important thing here is that the SMILE implementation, that's why it's called the SMILE random forest, uses the Gini impurity criterion to split each node. And the variable importance, as you can see here, B1 is 4,664 point whatever, and so on. Those values are the sum per variable of the Gini impurity decrease. So it tells you which the B2, the band number 2 in this case, experienced the largest decrease, or it explained the largest decrease in Gini impurity. This isn't the same as the usual accuracy criterion in other random forest implementations. This version was chosen because it is faster and less computationally intensive, which is useful because Google Earth Engine does give you certain limits on your computation. Otherwise, one user could, block the the platform for everyone else. So if you want more precise feature importance values, it's more useful to implement a local random forest based on data you downloaded from Google Earth Engine. But for a first look at what is probably the importance of each feature, the random forest implementation here is usually satisfactory. Then we go on. We want, of course, only to check for vegetated area what is the leaf area index, as a building will hardly have leaves to get biophysical parameters for. So we use a land cover product, in this case from Modis, the MCD12Q1. We use the product for 2015. Remember, we've got 2015 and 2016 as the years. So if we wanted to, we could also take some sort of mean from the 2 years, but in this case, we'll just go with 2015. Then that product has 5 different land cover computation products included in it. We want the type 5, which is the FAO. No, it's not the FAO. Anyway, you can check the documentation on the product for the precise definition of what each of these land covers are. We can also check while you're here is if you scroll further down, these tables tell you which particular values for each product mean what. So for our land cover type 5 product, 0 is water bodies, then come a bunch of different vegetation types, and then from 9 onwards, it is again non-vegetation. So we define a vegetation mask, which is greater than 0, but lower than 9. So that we only get vegetated areas. Then we apply this mask. Well, okay, this is a longer function chain over our image collection. As you can see, the mode is filtered, gets a map with various function steps. First, we need to scale the image, as was mentioned earlier. The MODIS data ranges from 0 to 10,000 for reasons of saving storage efficiency. But we want it in the actual reflectance value, so we have to multiply it by 1e-4 so that it is actual reflectance. Then we want to mask the values with update mask that only leaves pixels with vegetation, or pixels that were unmasked to be further used in the mapping function. Then after the update mask, we immediately classify with the trained random forest model, and we rename the product LAI so that it makes it easier for us later on. The function returns the products that have been, or the map that's been produced by classifying it with a random forest, and it gets the system time start again so that we can more easily use it later on. For the next step, which is we want to create a chart, a time series chart, I believe is the next step, yes. This time series chart for a certain area, the export area, I'm not sure if that's been defined yet, but it is, you can choose whatever area. There's actually handy tools in Google Earth Engine on the left top of the map, which give you different geometry drawing capabilities directly in the interface. So you can define your export areas being whatever suits you. Of course, the larger it is, the more computation it takes, and at some point it'll be too large. Then you have to decrease the resolution, or you have to decrease the size of your area. Yeah, but that of course depends on your application. So we've now defined point sample as our area. So we'll need to, because the region will be point sample. The image collection that we want to get the chart from, the time series chart from, of course, is the maps that we've produced. The reducer we'll use is first. That just gives you, well, we only have one piece of information per time step in our image collection. So we just use that. That is the first. So we just use the reducer first. And the scale, we'll use the native MODIS scale of 500 meters per pixel. Yeah, in the set options, you can change the way that the time series is shown. The important thing is that then we need to add the chart to the map itself. First, you can style where it is and how large it is, and then you can use the usual map.add, but in this case, not add layer, but add chart. So that should, once it's run, give you sort of a small chart inset in the bottom right. Also very useful if you create apps, GE apps, which is an option. You can you can make charts that pop up when your intended users open it. There you go. For this specific point, this is the LAI time series for 2015 and 2016 at the scale of 500 meters. Of course, if you choose a non-vegetated area, or one that's been masked out rather, then you won't have any information. That wouldn't make too much sense. Yeah. As a next step, we can also add our produced biophysical parameter maps to our LAI maps. Again, via the typical map.add_layer command. You have to set the opacity, all your things. As a band, we want the LAI band. As you remember, we named it so it makes it easier for us to remember what we've done. And if you run that again, then for the amount of pixels we are currently processing incredibly fast times, you get the maps over the 2 years. Yeah, I know this is for the first time step. As you can see, maps.first was selected. Yeah, by going through one image after the other, you can go through manually. But that depends on your further downstream processing chain. And similar to this, you can train random forests or other classifiers or regressors on loads and loads and loads of data. So you get loads and loads and loads of maps, and very easily and pretty much for free. That's what Google Earth Engine does for you. That concludes my part, and I think we have another quarter of an hour to answer questions, as far as I remember.
Thank you, Eric.
Thank you. Thank you to all three for your presentations and for the detailed explanation of examples that is especially useful. I have been answering some short questions on the chat, but I have seen once and again a comment on it's possible to have the full code snippet available. Will you share the code? I have answered that the recording will be available for the whole webinar in the YouTube channel. But if you want to
share, I have this one. Yeah, in Earth Engine, it's extremely easy to share the code. Just need whatever you have written here. The easiest way is just you click here in Get Link, and just basically I'm going to post it here, and then everybody of you that have Earth Engine account can access to the code and run it. So, and we can actually afterwards even to share it in the webinar, but or in any other places. But this link gives you free access to the code that we have just done here.
Perfect. And there is another question: what is memory limit? How to outcome this limit?
Pardon me, I didn't understand the question acoustically.
I suppose that the question is, as it's an anonymous participant, I don't know who is the person. It's probably that the person could explain more, but it seems that the person is interested in knowing the memory limits when working with this tool.
That depends because it's variable depending on the number of users that are using the application in that time. So first of all, we don't have that information. Is Google Earth Engine information. But I know under my experience that it is not the same when I work with the application when there are less users than when there are more users. Memories and computation timeout errors appear more often when users are using the application.
Yeah, it seems reasonable. Anyway, obviously it's necessary to try to know these limits. Also, I don't know if someone has more questions I can read here. Please, what are the purpose of taking only one single point? As the data is visualized on the whole globe, can you please repeat? Can we use Sentinel-1 and Sentinel-2? And moreover, Google Alpha Earth embeddings?
So in this case, we used, so thank you for the question. In this case, we visualized the time series for only one point because the example is just an illustrative example for this webinar to show you the power of Google Earth Engine. But of course, depending on what your interests are, you can define any number of points to show the time series for, or larger areas, which you can then reduce. For polygons that you define, you can reduce the image collection you have for that polygon using different statistical methods like mean or median and show the time series for that polygon. For example, you can sample from areas you're interested in and then show the time series over those samples. There's a lot of different applications. You can use Sentinel-1 and Sentinel-2 data. They are available in the Google Earth catalog natively. And Alpha Earth embeddings, I think there's a sample code available somewhere, but that's not the focus of this webinar. Thank you for the question.
Thank you, Eric. Another question is related to the ground truth information availability. Where did you collect the training sample? Is it ground truthing or remote sensing training sample?
Yeah, I can help with that. I thanks for the question. Yeah, that's kind of the purpose of these radiative transfer models. is basically these models emulates the behavior of the illumination and the reflectance through the canopy of the vegetation. So the truth are the results of the model. So this is why these approaches are so powerful, because you only need to tune them to the reality. So the vegetation of the canopy should be realistic, and the reflectance that they are providing are the truth and the information you try to invert. So these models per se are openly available in many ways in Python or MATLAB or other programming languages you want. And you basically go to a field campaign, you measure the chemical components of your vegetation, and you create your own samples. Then you, with this data, you train your machine learning model of preference, random forest, super vector machines, or whatever you want. So this is why we don't have field campaigns. What the people do in any case is because these leaf-array index measurements are very costly, are not widely available. You use some of them which are available in certain areas to validate that the retrievals you're obtaining with these RTMs are good enough. But you don't have enough data to create a model itself only with ground truth observation. That's the purpose of these RTMs we have just shown in this tutorial.
Thank you, Álvaro. Sorry, Emma, that I interrupted you when you were adding something to the previous question.
Yes, because related the use of Sentinel or embeddings, you need to consider that the data is preparing to working for some specific reflectance values. So take care when you would like to take the code and extrapolate to Sentinel-1 or embeddings or something like that, because the reflectance values come from the model, the RTM models. Just commented that.
Thank you. We have more questions. Why we use first function with the collections?
I can take that. In this case, we use the first functions not for the calculation or the training of the random forest or the production of the LAI maps. We use them only for the visualization in the JavaScript Google Earth Engine IDE, just to visualize one single image at one time stamp. Of course, if you want to download or use all the time series, otherwise you can do that. You can also loop through the image collection if you really want to, but it doesn't help you much more than that. You can use statistical operations to get a mean over the time series or that sort of thing. But for visualization in the JavaScript, using just the first image or whichever single image you want makes the most sense. But it's easy to produce all of them.
Mm-hmm. Also, related to data, some deep has a question. Dear professor, I have questions regarding rain period. I'm working in a part of India where 6 months we don't very less or no data because of cloud covers. Yeah, he hasn't enough information on rain, and he asked, can you suggest something to have more detailed information of these parts that are covered with clouds? It's possible to have additional information, or I don't know if you have comments for these parts that are covered with clouds. I can understand the intention of the question, but more or less.
Yeah, I guess that the question is related with what we can do when we don't have data, right? Because it's just kind of the problem of optical remote sensing is that we are not transparent to clouds. So every time we have a cloud, we cannot see through that cloud, right? That's when the users usually try to find solutions. In our case, we created our algorithm that I mentioned before to fuse MODIS, Landsat, and Sentinel data There are algorithms available. They're like Star FM, which is one produced by the NASA people, I think, which is not implemented in the engine, but there are an offline solutions to do that. You can also try to use other sensors like microwave sensors in order to maybe retrieve what you are missing in the optical part of the spectrum. I mean, this is an open question and there is not like a final solution, but definitely you need a methodology or an algorithm in order to gut feel or to interpolate this missing data that you don't have just because you are using optical data only from one sensor.
Mm-hmm. So in this case, heterogeneity of data need to be used for solving this problem. And it's possible to train gradient boosting models in Google Earth Engine like SGBoost, LightVDM, or CatBoost, and deep learning models like neural networks. Thank you. Very interesting presentation. Jose Esteve.
Thank you for the question. You have, I'm looking for the function because I don't remember all the names. Gradient tree boost classifiers. So in that case, it's possible to use the gradient boosting. Regarding to neural networks and deep learning, in that case, is not available in the Google Earth Engine application. In order to use deep learning, is needed to use Google Cloud, and in that case, you need to take care with the cost of the cloud.
Mm-hmm. Thank you, Emma. What would be the proper approach to recognize and classify the deciduous broadleaf forest in tropical region? This is a very interesting question from the research point of view, but it's not easy to answer. It could be it's very specific of the problem, I guess.
Yeah, yes, it depends on the method. You can use deep learning approaches, maybe running part of the code in Earth Engine, other parts in Google Cloud, and hosting that model there. You need also very good, valid, ground truth data for these classification approaches, maybe fusing sensors. I cannot give you like an easy solution because that's actually a very complex topic, especially because tropical regions are very challenging because of all the clouds and everything.
Yeah, especially to distinguish the different types of vegetation, and the problem is huge. And another question says, Dimitris Paronis, could you provide some metrics for the precision of the model obtained? Could you provide some metrics? I don't know if it's in general from the tool or for the particular problem that Eric was presenting.
There are not implemented for regression any statistical value, but all of us know the equation of the root mean square error or the mean absolute error. So in that case, it's possible to implement it in Google Earth Engine and then obtain a statistical value to measure the regression models. Regarding to classification, is easier because they have overall accuracy and kappa functions. So in that case, it's easy to give an answer in that case. In a question of a regression model is needed to implement by the user.
Related to the clouds that we were talking previously, Ousmane Lee says, thank you for your presentation. Is Google Earth Engine able to remove cloud properly, or is kind of a makeup that introduces more errors in the images? I don't know if we have some information on the capability to remove clouds, if there is any function to remove clouds, at least if there are no especially dense, or it's related to the question that Álvaro answered earlier.
Yeah, I mean, this is an open question how to do that. I would say that, for example, because sometimes I have seen that there is a strong interest about alpha Earth or satellite embeddings that you said. So, for example, if you want to classify a an easy way not to deal with clouds could be using the Alpha Earth model or the satellite embedded dataset. So you use this 64 bands, this embedding, which is not sensitive to clouds, and you use these features as these features for training your classifier. In that way, you don't need to deal with cloud contamination. It has benefits and it has drawbacks, but at least from a user's perspective, it will save you some time instead of dealing with this gap filling approach that we have mentioned before.
Thank you. Another question in the question and answer window is it possible to extract DAM's digital elevation models using Google Earth Engine? What are the resolutions available?
There are different DEM products already in cloud. I'm not very familiar to all of them, but you have, for instance, just putting in the search bar DEM, you can see that, for instance, you have from Copernicus a 30 meters digital elevation model, or you can find also Australian 5 meters digital elevation models. I'm not very familiar with all of them, but are available on the application.
Yeah, it's enough to search
and if you have a certain region of interest and you have a very high resolution DEM for that region and it works out storage space wise, you can also download that to your local and then upload it into Google Earth Engine and then use it as normal raster data there.
Thank you. Also related to data, how does LAI respond to climate variability over time using tubes, crew, and SID? What is the best data we can use for the global and regional or local regions? And how can we validate this with the ground? Many questions in one.
Yeah, that's interesting scientific question. Yeah. I think that there are a few papers, especially from creators of these remote sensing products, for actually analyzing variability of leaf area index related with climates. I think I'm mostly using well-established remote sensing products like the MODIS, FA-PAR, and leaf area index products. So yeah, I would suggest just to go to these papers and this analysis to check how climate affects leaf area index or vegetation at a global scale, which I think is the question here.
Thank you. We have more questions, many questions today. The next one, is there a roadmap for real-time collaborative coding in Google Earth Engine, similar to like Google Docs, to better support multi-user projects? Thank you.
I don't know, Emma, I can try to answer. I mean, I would say that not exactly in the same way, but for example, as this JavaScript environment I have shown, or we have shown here, is not as direct or flexible as this Google Docs thing, but it's true that you can share the links, and every script that you save in your account could be shared with other people. So the people can modify, save, and it automatically gets synchronized and control changed, controlled, so to say, in a Git. So I think even though it's not as powerful as a Google Doc or flexible, you have a lot of flexibility to work collaboratively with this kind of JavaScript environment. And on the other hand, if your choice is to work with Google Earth Engine in the Python IPA, you can use collab notebooks that you can share. So everybody can actually change the code and play with the collab notebooks in a collaborative way. So I think that these are probably the two approaches that comes to my mind, but maybe Emma can add some more about this.
Yes, also the scripts at the end are a GitHub repository. So at the end, you can share your repository with someone. I have different type of repositories that I share with Álvaro, and we work together. Is what Álvaro say is not the same than Google Docs at the moment that one is writing, you cannot visualize, you cannot see. But at the moment that the person save and you refresh, you can visualize the change that the other person did it. And in that case, it's the best way to work in a collaborative way at some point.
Mm-hmm. Thank you. There are some comments answering to other questions of some help offered by some of the participants to others. You can read by yourself the information. If you have made a question, please read the chat, because some help is there from other persons offering information on other research issues. I think that we don't have more questions. Let me check here. No, I have only a question, a very short question related to flexibility for execution of deep learning models. Is there support in Google Earth Engine for frameworks like TensorFlow or PyTorch, for example?
You can connect, but in that case, is what I say before. Is not directly available in Earth Engine, but you can use Google Cloud or deploy a virtual machine there, create a Jupyter Notebook script there, and training your model in the Google Cloud and connect with Earth Engine in order to inference a final map. But again, with that, I only can say take care, because the application is for free in the academic field, but the Google Cloud is not for free, so you need to control the cost of that, because it can be expensive.
Mm-hmm. Thank you. Well, all the questions are answered. Thank you very much, because we had many questions today. We have another one, the last one, and then we close. How accurately can machine learning models predict forest structural complexity using satellite-derived variables in Google Earth Engine? This is a very research, a very interesting question from the research point of view too, because it's not easy.
I'm going to answer that working with Google Earth Engine is equal than working in your laptop. At the end, you work in a cloud platform and you can scale your results. But this scale is making bigger your results. Another thing that is making more accurate or less accurate, that depends on your data, that depends on your model, that depends on your training way. So everything depends on the user at some point. So how accurate can be equal than in your own laptop at some point.
Yeah, it depends on the implementation, the data, the problem, and many things. Thank you to you all for first for thanks to the speakers for being here. It has been a pleasure as usual. We repeat that the information will be available in the YouTube channel of GRSS. It's in the chat, the information related to the channel. And thank you to all the persons that have been here attending the seminar and participating. It's all. Thank you very much. And see you. Bye.
Thank you so much for the
Thank you
invitation.
very much.
Thank you for attending. See you.
Bye.
See you. Thank you to all.